Last time, we saw the Lovasz Local Lemma, or LLL. The LLL was an existential statement. It says that there exists some assignment that avoids all bad events. Today, we'll see an algorithm to find such an assignment efficiently. First, recall the Lovasz Local Lemma from the last lecture. We have m bad events, a1 up through am, and we assume that for all I, the probability that the ith bad event occurs is at most p, and also that ai, the ith bad event, is mutually independent of all but d other events. If those assumptions hold, then we saw two different conclusions. In both of these versions, the punchlines are that if p and d are small enough, then there's some positive probability that none of the bad events occur. In particular, there exists a state of the world in which no bad event occurs. The question for today is, how can we find that state of the world efficiently? Today we'll see the algorithmic or constructive Lovasz Local Lemma, which will tell us how to do that. In order to introduce the algorithmic LLL, we'll need to introduce some notation. I'm going to introduce this notation over here, along with our running example of ksat over here. First, let v be a set of underlying random variables. For example, in ksat, v might be our set of variables that we're going to use in our formula. Let curly a be a collection of bad events that are determined by these variables. So for example, in ksat, ai might be the bad event that the ith clause is unsatisfied. Let variable of ai denote the set of variables that are involved in the bad event ai. So in ksat, variable of ai is just going to be the set of variables that appear in the ith clause. Finally, let gamma of ai be the set of all events aj so that the variables in ai and the variables in aj intersect. In the ksat example, gamma of ai is the set of all the events aj so that the clauses I and j share any variables. With this notation, here's an algorithm to find a way to assign values to all of the random variables in V so that none of the bad events occur. So given a set of variables V and a collection of bad events A, we're going to do the following. First, we'll choose a random assignment sigma. So for each variable little v and big V, we'll have some sigma v, which is just chosen randomly. Then, we'll just have a big while loop. While there is some bad event, a in curly a, so that a of sigma equals 1, that is, so that the event a occurs when the underlying random variables are set to sigma, we're going to first arbitrarily choose such an event, and then we'll update sigma by re-randomizing the variables that appear in that bad event a. That is, for every variable that appears in a, we will re-choose sigma v completely randomly. For example, if we were to run this algorithm for ksat, it might look something like this. Suppose we start with some formula like this. x1 or x2 or x3 and not x1 or not x2 or x4 and so on. Then the first thing we're going to do is choose random values for each of the variables. So, for example, maybe x1 is equal to 1, x2 is equal to 0, x3 is equal to 1, and so on. Next, we check and see which bad events occur. In this case, this clause turns out not to be satisfied. So the bad event associated with this clause does occur. Then what we're going to do is just re-randomize the variables associated with that clause. So maybe I'll re-randomize x1 and maybe it stays 1. I'll re-randomize x2, maybe that turns into 1. And I'll re-randomize x4, maybe that stays 0. Now I have a new assignment, and I'm just going to repeat again. Look for some clause that's unsatisfied, re-randomize, repeat. This is a very simple algorithm, but it turns out that it actually works. So here's a theorem. Suppose that A is a collection of bad events determined by random variables in V, like we had before. And suppose that all the bad events A in curly A satisfy the following properties. First, that the size of gamma of A is at most d plus 1. In particular, this implies that A is independent of all but d other events. Second, assume that the probability that A occurs is at most 1 divided by e times d plus 1. Then the conclusion is that, first, eventually, the algorithm on the previous slide will find an assignment to the variables in V so that none of the bad events in curly A occurs. In particular, there exists such an assignment. And second, the expected number of re-randomizations that the algorithm needs to do is not too large. It's bounded by big O of the size of curly A, so the number of bad events in question, divided by d, or d plus 1. It's a good idea now to pause the video and compare this to the version of the LLL that we saw last time. You can notice that quantitatively they're extremely similar. This is actually a simplified version of the algorithmic LLL. Here's a more general statement. The more general statement looks like this. Once again, suppose that curly A is some collection of bad events determined by random variables in V. And now suppose that there exists some map, little x, which maps the collection curly A to the open interval 0, 1, so that for all events A in curly A, the probability that A occurs is bounded by x of A, so this is just some number bigger than 0, less than 1, times the product over all events B in gamma of A, other than A itself, of 1 minus x of B. If this holds, the conclusion of the theorem says that first, eventually, the algorithm on the previous slide will find some assignment to the variables V so that no event in curly A occurs. In particular, such an assignment exists. And additionally, the expected number of re-randomizations that the algorithm needs is again bounded, in this case bounded by this quantity, the sum over all events A in curly A of the fraction x of A divided by 1 minus x of A. Okay, so this might be a bit hard to parse if you haven't seen it before, but to start to get some understanding of it, let's prove the simpler version from this one. To prove the simpler version from the more general or asymmetric version, we're just going to set x of A to be equal to 1 divided by d plus 1 for all of the events A in curly A. Now, suppose that the hypotheses of the simpler version hold. That is, for all A in curly A, the size of gamma of A is at most d plus 1, and the probability that A occurs is at most 1 divided by e times d plus 1. Then we can bound this condition that shows up in the asymmetric LLL. We have x of A times the product over B in gamma of A, not including A, of 1 minus x of B. Well, this is greater than or equal to 1 divided by d plus 1 times 1 minus 1 over d plus 1 to the d. Here we're using this assumption to say that there are at most d things in this product. But now this is greater than or equal to 1 divided by e to the d plus 1, using the fact that this quantity here is always greater than or equal to 1 over e for any d. Thus, this condition here, the assumption for the simpler version, actually implies this condition here, the assumption for the more complicated version, and so then we can apply the more complicated version to conclude the simpler version. So this proves the simpler version from the more complicated version. Whether we're looking at the simpler version or the more complicated version, this theorem should be pretty surprising. This algorithm here is so simple, and yet this theorem says that it works, basically whenever the original LLL applies. Now that we understand this algorithm and the statement of the theorem that it works, it's time to prove it. We'll do that in the next video. In the next video, we'll sketch a proof that this algorithm actually works. See you there.